Let's apply the model of motion in 2 dimensions to an object moving, a projectile starting out with some velocity v0 at some point, and we know that the projectile is going to follow a parabolic path. Assuming this is an ideal projectile, 0 acceleration in the x direction because there's no force in the x direction, and acceleration of gravity in the y direction, and it's downward. We're going to set up a coordinate system, and we could set it up from any point we wish, but we're going to go ahead and set it up so that the origin is at the intersection of the plane on which the projectile is going to land and the line that intersects that plane directly below the initial point. So here's the origin of our coordinate system, and we can say, okay, here's some successive r vectors, not necessarily at equal time intervals, certainly not at equal time intervals, because in equal time intervals, the x displacement from here to here would have to be uniform. Well, the displacement between here and here is less than it was here. The x displacement between here and here is pretty small, much less than it was here. And the x displacement on equal intervals is clearly going to be approaching 0 if we keep making uniform or even decreasing distances along the arc. That's not particularly important, but it's something you kind of want to be aware of and you want to think of. So those are not positions at equal time intervals. They certainly can't be if we have uniform motion in the x direction, which is the case. Not uniformly accelerated motion, although it is uniformly accelerated. The acceleration is 0, so it's just plain old uniform motion, uniform velocity in the x direction. And if these are at equal time intervals, that's not what we have. In any case, these are our r vectors. Okay, so here are some r vectors at different times. Now, what's the situation here? The situation is that the acceleration as a function of time is 0I minus g times j. No acceleration in the x direction, ideal projectile. Acceleration of gravity in the y direction. Okay? Now, what do we get if we integrate that? Well, v of t is going to equal what I've called in class cxi minus gt. Let's make that a plus a negative gt plus cy in the y direction. Okay, fairly simple. And we have the condition. Now, we haven't said what the initial condition is. Let's assume that this distance of descent here is delta y total. So from here down to here is your delta y total. And let's just say that distance is a delta y total. This is just the distance, the magnitude of your displacement. And we'll bring that around in a little bit and be more specific about the vector displacement. But now we can say that we didn't really need this here. What we need is the v0. And let's just say v of 0 equals v0, which is some v0 x times I plus a v0 y times j. So our velocity times 0 is this. Well, if we use this condition with our velocity function, our v of 0 has to be cx times I plus negative gt plus cy times j, and that has to equal v0 x times I plus v0 y times j. Well, v of 0 means that t equals 0, so this is v times 0. This implies that cx equals v0x and cy equals v0y. Because, of course, the I components have to be equal, so v0x has to equal cx. The j components have to be equal to 0. Well, g times 0 is 0, so cy has to equal v0y. So now we know that our v of t function is v0x times I plus negative gt plus v0y times j. So our integration with our initial condition that we have initial velocity v0 gives us our velocity function. Now we integrate this along with the condition that our initial position be what? It's going to be delta y total times j. Okay, the vector from here to here. That's our initial position. And we could actually sketch that vector. This is our r of 0 vector. This vector from here to here. So our r of t vector is going to be our integral of our, and that's a vector v of t vector with respect to t. That's going to be the integral of v naught x I plus negative gt plus v naught y j with respect to t. And that's going to equal integral of v naught I is going to be v naught x times I. It's going to be v naught x plus, I'll use cx again, not the same as the cx I used here, and the cy I'm going to use in a minute. It's not the same as the cy I used here, but since we've already evaluated these, we can reuse the variable name. So it's this times I plus, well, the integral of this with respect to t is negative g t squared over 2 plus v naught y t time, and jump the gun there. We have a cy times our j. Then we use the condition that r of 0 has to equal delta y total times j. Okay, this vector. And that has to equal, if we substitute t equals 0, and gee, I didn't put my t in here either, being pretty careless. Okay, if we substitute t equals 0 up here, we just get that r of 0 has to be cx times I. And then t equals 0 here is going to make this term and this term 0. So it equals cyj. Well, that implies that cx has to equal 0 because we've got 0I component for r of 0, and cy is going to equal delta y total. So that r of t is going to equal, substituting cx equals 0 and cy equals delta y total, v0x t times I plus negative gt squared over 2, bad looking g there, maybe a little better, plus v0yt plus delta y total times j. Now we have our position function corresponding to whatever our initial conditions are, also our velocity function.